All right, so hi everybody. I'm David. I lead architecture for a company called Proofpoint. We work on security products, cloud security products. And the reason this is relevant is because I'm going to be talking about observability in this talk today, and a lot of the stuff I'm going to talk about comes from a lot of painful experience over the past couple of years. Because when I joined Proofpoint, it was about 2 years ago. That was a while after we acquired a startup which built the core of the product I'm mostly working on right now, which is called CASB, Cloud Access Security Broker. Basically, it listens to a bunch of events that happen on cloud services like Google Drive and Office 360, does a bunch of processing on them, and tries to find attacks on cloud infrastructure and cloud accounts. And basically, it's a big data processing architecture. And when we bought the product from a startup, it was built very much in startup mode, which hopefully, and all of you know what it's like. When a startup, you're trying to find a market fit, and you're trying to figure out the product. And so it's always built with features in mind, right? Because you need the next feature, you need to bring in the next customer, the next sale, and stuff like technical debt and scalability and stability and stuff like that. That kind of takes a back seat to just getting the features out the door as quickly as possible. I'm not saying this in a negative way. That's how you build a new product and how you sell it. But once a big company acquires it and it said, okay, well, we're going to take this and then scale it out to 1,000 customers, that's where you need to switch from startup mode to enterprise mode, which is you have to build in scalability and stability and figure out all the weird bugs that happened that nobody ever addressed. And that's where you actually have to start building enterprise features into your product so it can actually scale to serious customers, people who expect the product they paid for to actually work in production. And this is pretty much when I joined Proofpoint, right? And so we took this very shaky, often downtime in production kind of product, and we gradually evolved it towards something that's actually very stable today. We sell it to thousands of customers, and it works pretty well. And so there was obviously very painful journey with a bunch of effort in the middle. And the main thing I want to talk about, which is observability. So before we start talking about observability, I just want to demonstrate what observability is. How many people here work in a product that's in production right now? Any kind of code. So most of you, as expected. Perfect. How many people here, without looking at your phone or internet or anything, can confidently say that the system is now working and there is no problem? Anybody? Like 1, 2, 3? But notice I'm not raising my hand, right? Because without looking at my phone, there's no way to know. It's on silent. Okay, so let's make it easier. How many people, if you can look at your phone for 1 minute, who would be confidently able to say their product is working? Okay, that's a lot more people. What if I gave you a laptop, an internet connection, and 10 minutes? Who would be able to say if their product is probably working? Most everybody. Okay. So this actually gives you a very good feel of what observability is, right? And that's the feeling of confidence that the thing you built is actually working as expected. There's one guy in the back still going like, yeah, I forgot. That's me too. And so it says, observability is basically the feature of a software system which tells you about the inner workings of the system, whether it's actually working correctly or not. And that's, you measure observability in this confidence of, yes, I know my system is probably okay. If it wasn't, someone would tell me. And hopefully fix it automatically. That's like the holy grail. So yeah, that's pretty much it. That's like my definition of observability. It's not a binary thing. It's not like your software has observability or it doesn't have observability. It's a scale. And the goal is to increase the observability of your system and thereby reach a point where you're confident that the system is working. Now, this isn't something that we do just because we like it, right? We don't build stuff just because, okay, to be fair, we do build stuff because it's cool. That's all the whole conference is about, basically. But the primary reason of why you actually want observability in your system isn't just because it's cool and you get to play with new technologies. It's for business reasons, right? That's the reason most of us come to work, is because we work for a company that sells something, and serious customers pay money for this something, and they expect it to work, and that's eventually what pays our salary, right? Anyone who doesn't feel that, I'm sorry. So the reason we actually want our system to be stable is because this is the product we sold to our customers. Ultimately, being able to confidently say that my system was working is just as important for a product as having a nice UI or having whatever business features you actually sell, right? Having observability, good observability, leads to a better product, something stable, something that's really customer facing, that you deliver value to your customers. If you have poor observability, you really can't tell if at any given point in time that you're actually providing the value that the customer paid for, in our case, a lot of money. So this is why you want it, right? You want to know if anything is actually currently wrong, and if something is wrong, ideally what you want is you want to know exactly what's wrong, why it is, and hopefully how to fix it. And in the best world of all possible worlds, you want it to happen automatically without you having to wake up in the middle of the night and actually fix it yourself, right? And so when we talk about what observability is and why it is, oftentimes we run into these so-called 3 pillars of observability. Like if you look at blogs and meetups and stuff, there's a lot of talk about observability recently in the past year or two. Right, so because you know how things in tech go in cycles. Like 10 years ago, all conferences did microservices. Everything was microservices. How do you break up monoliths into microservice? Right, and so we did that. And then a few years after that, it was all containers. Like we have all these microservices. How do we deploy them to production? And so everything was about containers and Kubernetes and orchestration and blah blah. And so we did that. And now we have all these containers in production, but we have no idea what's going on in the containers. And are they up? Are they down? Is stuff broken? And so now we're going towards this year or two where everything is going to be about observability. How do we observe our system? Right, and this is why the talk is now. 2 years ago, I did a talk about containers, obviously, because you have to follow the trends. I don't know what's going to be next year, probably AI or something, or blockchain. No, blockchain is past, probably something new. So anyway, so when we talk about observability now, most of the conversation is driven by vendors, right? So someone wants to sell a product, and they say, okay, well, my product does log aggregations, and that's how you get observability, right? And so you go to some other blog which says, well, we solve this thing that does metrics, and that's how you get observability, which is kind of yes and no. That's not the way you need to think about it, right? Observability is, I have a business problem, which is I sold something to a customer, and they expect it to work. How do I do that? And some of the technologies that allow us to do this better are using logs, using metrics, using traces. But there's like a whole other group of things that also help this, right? For example, having a CI/CD pipeline, having deployment, right? Connecting. Ideally, you would like to know that if there's a problem in production, a deployment happened 1 minute before that, and you want to correlate those two, right? And there's stuff like automation. For example, if you know that a service is overloaded, ideally what you want to happen is it will automatically be taken care of. And there's a whole bunch of stuff tied into observability. It's not just these 3. But to be fair, those are the 3 primary technologies we want to use to improve observability in a system which has very low observability. I'm going to keep saying observability until the word loses all meaning, by the way. There's like 500 occurrences of the word in my presentation. So bear with me. So that's not the only way to do it. For example, in our case, the system I work on mostly, the way we get observability is not using traces, right? We use our logging system to also overload it with traces, and we'll talk about traces in just a bit, right? So you don't have to have metrics and logs and everything together. You can define what goal you want to have, like what is important for your system, and then you figure out what tools you want to use and what technologies you want to implement to get there, right? To arrive where you want to have confidence that every service is working, data is flowing, all the databases are databasing or whatever. And so in order to do that, the first thing that you have to do is define your objectives, right? This is a business problem. Again, I'm going to keep going back to this. Observability is a business problem, first of all, and it's a feature you add to your product. And so before we get into how we get observability, we have to define what is it exactly that we promise to our customers. This is where words like service level agreements, SLAs, right, come into play. So for example, in our case, we sell a product to a customer, and we're contractually obligated to provide our service within X milliseconds or X seconds. And we promise to have uptime of whatever, 99.9.999% of all the time, right? And so it's different for every service, and whatever makes sense for your product, that's how you define the SLA, the service level agreement with your customers. It might be explicit in your contract. It might be implicit, right? You sell something, and it's understood that it kind of works, and what the things you need to do in order for it to prove that it works. But once you have this service level agreement, you define what it means to have your product working, then you start defining what the objectives are. For example, a common SLO would be, I want my web page to load within 2 seconds, 99% of the time. Right, so the 99th percentile latency of my web page should be under 2 seconds, right? So that's a service level objective. That's something I can define. I can now start measuring things, and I can say, is my system behaving within this metric, right? And so I can have a service level indicator, some kind of metric which tracks page load times. I can track it over time. I can look at a month back and say, okay, over the past month, did I hit my service level objective? Did my service actually load the page within 2 seconds, 99% of the time? If the answer is yes, great. If no, I need to go and fix some stuff, right? And so that's the way I think we need to approach how we want observability and where it's important to find observability, right? Because maybe the page load time is directly related to how the database works, and that's where we need to focus and optimize. And maybe it's related to whatever technology we use for the web server. It doesn't matter because we're looking at the symptom. We're looking at this is what we mean when we have our objective and our service level objective, and that's what we actually want to optimize for. So another common example in our system, for example, so we have a distributed data processing system. We have a bunch of services sending Kafka messages to each other. Everybody knows what Kafka is, right? Raise your hand if you don't know what Apache Kafka is. There's one troll in the back going like, I don't know it. He knows it. I know him. But okay, so we have like 60 plus services, and they're different applications, and they talk to each other by sending Kafka messages. And so our end-to-end latency in the system can vary very much depending on which route any message takes through the system. So one type of message can go and touch 20 services, and another can touch 50 services. And so for us, a very important metric is what is the end-to-end latency in our system, which is something that's very hard to measure when there's no one thing to measure. It's 50 different variations. And so we can go and actually use a bunch of technologies that I'll talk about in just a bit to slim it down to just one or two things we can measure and then say, okay, this what defines good performance in our system. And if it's outside the bounds we decided, either we need to calibrate because maybe we were too optimistic and we need to increase the objective. Maybe 2 seconds is optimistic, we need to go to 3 seconds. Or we can say, no, 2 seconds is what we want, and we need to go and optimize until we reach that objective, right? And so this brings us to, okay, so how do you know it's working? So I want to show a few examples. This is a bad example. I'm just going to say, but by the way, disclaimer, if there are any current or future Proofpoint customers listening to what I'm saying, please realize anything bad I say is in the past, and currently everything works great. Okay, just to be clear. But this is a bad example. This is one of our indicator dashboards from about 2 years ago. And we iterated on this quite a bit. It doesn't work like this anymore. But this was on our wall on the monitor, right across from where our manager sat and where our product people sat. And this pretty much defined what we cared about at the time. So our business people cared about exactly, whatever, multiply that by that many things, and that's what defined if the application is working, right? So in this case, there's a list of customers. We didn't have that many customers at the time, and so we could actually have a rotating list of the most important customers. And for every one of the customers, we had one specific metric for every feature in our product. And if it was green, everything was good. If it was red, we need to figure out why it's red, right? And each one defines, as an example, I obviously hid the customer names, but the top line customer, I caught the system in a very bad day, by the way, for the screenshot. I waited until something was broken, and then I took the screenshot. So for example, in this customer, we can see that there's no file events for the past hour, which indicates that there's something broken in our pipeline, and we need to go and fix it. And so the good thing about this indicator dashboard is it tells us which customer is affected, so customer support can go and notify the customer that they're experiencing degradation. It tells us exactly where to look for the problem. It's somewhere in the file subsystem. It's not in the login event. It's not in something else. It tells us where it is. And there's a very clear indicator. It's either green or red. There's no guessing. There's no graph that you need to look at and try to figure out, does this look okay to me? Right? So it's very clear. It's very obvious. Now, there's obviously bad things about this. One is it's not really customizable. It's hard-coded things. We need to iterate on it quite a bit. And also, it just doesn't scale. You can't show, now we have thousands of customers. There's no way to show thousands of customers in this way. So we moved to other ways of actually getting the indicators. But like when you're a small startup and you're just starting, and you have 10 customers and you really, really care about keeping the customers happy, this is a good way to do it. Right? You have your 10 customers, you know exactly if one of them is unhappy. And you have to go and tell them. Right? One of the things about observability, which I didn't talk about, but one of the key parts is you have to be transparent. You have to go and tell your customer. The worst possible way to discover a production problem is, okay, I'll tell you a story. I usually don't tell this. So like 2 years ago, a few months after I joined the company, we discovered the production problem in the following way. Our VP of sales was giving a presentation to a huge bank. In the middle of the night, because our R&D center is in Israel, he was doing it in the US. In the middle of the night, he called my director of R&D to ask, why is the demo website not loading? And is that normal, and do we know about it? And we didn't know about it, and it wasn't loading, and stuff was broken all over the place. And so that is probably one of the worst ways you can find out about an issue in production. Right, and so you want to know about issues in advance like this, and you want to go and you want to tell the customer before the customer asks you about this. Right, so a different example is, last week there was an outage in AWS in Frankfurt. One of the availability zones in Frankfurt had a network partition, so they have AZ, A, B, and C. And so AZC couldn't communicate with availability zone A and B. Right, and we discovered it about a minute after it happened. And so 5 minutes after this happened, we had a Teams channel open, we have the Zoom video call going on, and we had the head of our DevOps and all the engineering managers in the call already discussing how we're going to communicate this to our customers. Right, so that was very fast, less than 5 minutes from when it happened until we actually had like a war room going and trying to figure it out. And then 20 minutes later, on the AWS status page, it changed from green to red. Right, so that's not the way you want to communicate to your customers. Now, to be fair, this might be a business decision. Maybe Amazon knew about it right away, and they just didn't update the status page for business reasons. That's perfectly fine. I don't know what's actually going on inside, but that's the main difference, right? So this is a good example of, we found out about this way before the customers. Our customer success people sent an email to all the customers that we're experiencing degradation because of Amazon, and this is what the steps we're taking to resolve it. And like the absolute worst example was the first one, which was from 2 years ago, and stuff just broke and we didn't know that, right? And there's like the two opposites, and you want to slowly go from one to the other. There's no way to jump from the bad example directly to the good example. You have to build a bunch of steps along the way. Right, this is another example. How many people know what Reddit is? People read Reddit, yeah? So this is the Reddit public status page. They're using an application called Status Page. Everyone can use it. It's, I think, free for personal use. And so this is their public status page, and it shows exactly what people who use Reddit care about. Is the website up? Is the mobile app up? Native mobile app, vote processing, error rate. There's very specific, very clear indicators, and you actually have a history of those. And if you really, really care about Reddit's uptime, you can even subscribe to notifications. I don't know if anyone does that, but like maybe if you're a hardcore enough Redditor, you can subscribe to Reddit uptime notifications. So again, this is a very good example of something that you want to show to your customers and be transparent with your customers. But this is not how you start, right? If your system goes up and down all the time and it's broken because you just finished building it, the first iteration of it, you don't want to immediately put up a public page, because then your customers will all see how much your system is going up and down. You have to first build internal observability tools and fix all the stuff along the way, and then eventually you go to the transparency page. You don't start with the transparency and notifying customers before you fix all the other stuff that's broken. Right, and so let's talk about how we actually get there, right? The actual technologies and the actual tools we can use to get observability built into our systems. Before we talk about this, let's do a small experiment. Of the people earlier who said they have a production system, how many of you have centralized logging in your system? All the logs go to like a central place. You can log into there and search all the logs. Probably like Splunk or Elk, Elasticsearch, stuff like that. Very good. How many people have centralized metrics, right? Somewhere you can go and look at all the graphs and pretty charts and stuff like that. So fewer than logs. How many people have distributed tracing as a separate subsystem? And again, before you raise your hand, distributed tracing in this case is not traces, as in like system traces. It's where you can trace a transaction in the system from end to end, and then get the entire trace log and look at it in one place. Right? There's like 3, 4, about 10 people. Right? And this is about how it goes mostly. Everyone has logs. Logs is like the oldest technology there is. In the dawn of time, when we invented computers, and like the first Neolithic programmer picked up 2 rocks and banged on the keyboard, and they banged out "Hello World," and then he compiled and ran it, and it didn't work, right? And so the next 2 lines in history were print before hello and print after hello, right? And that's how logging was invented. So like logging is a very well understood technology. Metrics is usually right after that. Normally people start with system level metrics like CPU, disk utilization, stuff like that. And then you work up to more advanced application level metrics, stuff that's actually specific to your application, like how many requests per tenant or per user you're doing, what kind of errors there are, right? More advanced kind of metrics. And then after that, if you have a complex enough system and a large enough system, then you advance towards having distributed tracing, because if the system is complex enough, it's very hard to figure out. Even though every service is reporting as healthy, there could still be things end-to-end that are broken, right? And that's where you move towards distributed tracing and trying to figure out holistically how transactions work in your system, right? And so we'll talk about all of those. We'll talk about how to tie them all together. And I want to start with metrics, because metrics are fairly well understood. Most people who voted probably have like Grafana or Prometheus or one of these common tools, and you have a bunch of dashboards. And the benefit of metrics is they're very cheap. Compared to all the other technologies you can use for observability, metrics are by far the cheapest. You can store a lot of metrics, mainly because they're aggregated and they're time series samples, and there are very efficient ways of storing time series data. There are databases that are optimized just for that, and unless you have just millions of metrics, each unique metric is very cheap to store. Usually what happens is you collect a bunch of samples. For example, you sample the CPU every millisecond. And then you take all these 1,000 samples per second, you send them to some kind of sampling aggregator, and it averages them out and stores one sample for just that 1 second, right? And so it compresses it down by a factor of 1,000. Or maybe it stores one sample per minute, because it's not something that fluctuates a lot, right? And so metrics are very well aggregated, they're stored, and so you can store them forever, right? In our system, we have a year of metrics back, right? We don't delete them. And so, because they're aggregated, you can actually store them very long. You can zoom in on metrics. You can have a lot of them up to a certain limit. And they tell you a lot of interesting information about your system, right? And so usually you start with the baseline metrics like CPU and load, and then you progress to more advanced application level metrics. So I'll give some examples in a bit. What's the problem with metrics? There's a downside with metrics. They're not very detailed. I'll give an example. We had a weird bug a while ago. We had a bug where every few seconds there would be a latency spike, right? And we go and look at the graph of requests, and it's completely flat. There's average requests going on, nothing weird. Look at CPU load, it's completely fine, looks flat. We look at disk, every cunning metric you can think of, and we couldn't figure out why there was latency spike in our requests every X seconds when the rest of the system looks fine. And so we spent several days on trying to debug this, until we actually decided we'll increase the resolution for our metric collector. Instead of sampling and then aggregating down to 1 second, we'll sample it every millisecond and figure out what's going on. And that's when we discovered that it's not completely flat. The metrics are all over the place. And what was happening was the garbage collector would kick in every few seconds, and then all the web requests would queue up. And then when the GC finished, all of them would happen all at once. And that's where the latency spike comes in. And so there was no way to discover this problem just from metrics. We had to dig through logs and then increase the metric resolution to actually discover this. But you can't do this everywhere, right? You can't store very high detailed metrics everywhere. So that's the downside. You can't get perfect visibility just from that. So if you don't have metrics, or if you have like we had initially, every service had whatever metrics someone figured out they would need, right? You want to get to a consistent state where you have a common set of metrics you collect for every kind of component in your system. I say service a lot, but it's whatever, component, module, services, whatever is your thing. If you do monolith, then every component in the monolith. And so these are what's called the 4 golden metrics. The name is straight out of the Google Service Reliability Engineering book. I highly recommend everybody should read the Google SRE books. There's a link downstairs, or if you just Google for Google SRE, that's the first link. And it's a set of 2 books that talk about the service reliability practices at Google, which is the company that pretty much defined service reliability. And it's really interesting and again, very educational to see how they think about reliability and observability and stuff like that. And so this term comes directly from the book. And what it means is there are 4 metrics which you want to collect for every component in your system. And there are latency. Latency is how long a single transaction or request takes in that system. If it's a REST service, then the REST request. If it's Kafka-based service or a queue-based service, how long it takes to process a message. Traffic, which means how many requests it actually gets graphed over some interval. Error rate, so our percentage or absolute rate of how many of the requests actually result in an error. And saturation. Saturation is how much of the critical resource your component is using. So for different components, It might be different resources. Some it might be CPU or disk utilization or network. But whatever is the bottleneck for that component, how much of that is the component using? And if you track those 4 signals for everything consistently in your entire system, you will cover a significant percentage of all the possible problems you can experience. There's like the golden 80-20 rule. Like you'll cover the 80% of different issues just by watching for these 4 things everywhere, right? There are different ways of looking at it. There's a thing called the red metric technique, which takes just 3 of those and ignores the saturation. There's different ways of thinking about it, but generally these 4 cover most of the things you want to track in a service, right? Also, you can get most of those just from the operating system. You don't need to do any special work, right? So things like latency, you cannot, because latency is specific to the application. But saturation, you can definitely get from your operating system. Things like traffic and error rate, if it's a web-based system, you can get from the infrastructure. Like if you're on Amazon or Azure or Google Cloud, the load balancer will just give you these metrics for free. You don't need to do any work to get them. You just need to track them and get alerts going, but you don't need to do any work. And latency depends how you measure it. For a web-based system, you can even get latency for free out of the infrastructure. And so it doesn't really cost you anything as long as you do this consistently. It took us a while to get to a place where every new service automatically had a dashboard with these 4 on them. But right now, a developer can go and create a new service in production, and something will automatically create a dashboard for that service which tracks these 4 things. I'll actually show an example in just a bit. And so the other 20%, that's where you cover with application-specific metrics, right? And there's no golden rule for that. So in some cases, it might be stuff that's actually business-related, right? For example, I want to see how many transactions happen in this service per customer. Or in our case, there's a good example. We have a business rule engine that runs kind of some sort of heuristics, and the customer creates rules for it, right? And so normally, it spits out alerts very infrequently. It's like 1 per second. But if the customer misconfigures something, it will suddenly start spilling out a lot of alerts. And so there's no way to get this from the system metrics, right? We need to go and add a specific metric, instrument the code, and add the specific metric in the code that says, this is a metric of alerts per customer, and we can add a system alert on our side if the alert average changes by more than 100% within, let's say, 5 minutes. Then we need to check and see if the customer misconfigured something, right? And so normally what you do with metrics is you put them on a graph or a dashboard, right? How many people have a dashboard that tracks something, metrics? Most people, right? And so it usually looks something like this. I don't expect you to see anything here, right? This is a specifically bad example on purpose. This is a very old dashboard. It doesn't exist anymore. It was one of the initial dashboards we had for tracking a specific system in our application, in our product, which does rule evaluation. And you can't get anything out of this dashboard, right? This was built organically over time. Whenever some engineer needed to solve a problem, he'd go to this dashboard and add another graph, and add another graph, right? This is terrible, right? I know every one of these services, and I can tell what's going on, right? So this is a bad example for several reasons. One, it doesn't track the things you want to track. It doesn't track load for all services. It tracks random things. One graph is the lag in Kafka for one service, but not for other services. One graph is the load for a specific service, but doesn't show the load for other services. It's all over the place. It's a very bad example. And so let's switch to the opposite of that, which is a good example. This is a dashboard for one of our recent services. First of all, much more colorful. Colors are good. I'm not kidding. It's not like kindergarten stuff. Colors are very expressive. You can very clearly see when there's a problem, right? There's a dashboard and it says there's a red square. You immediately want to click on the red square, right? This gives you very clear indication of there's a problem. Click on this. It will zoom in on the problem, right? This is the kind of stuff you actually want when you go and investigate a problem in production, right? And so this has the 4 golden signals. It has traffic. It has latency. It has saturation, which in this case is load, and it has error rate. Right, and this dashboard we have for pretty much every service, and you can go to that and you can actually get alerts out of it. So you can't quite see it, but there's a red line on every one of these graphs, which defines thresholds for what's normal for the graph. And if it goes above or below the threshold, depending on which, it actually sends an alert, depending on the type of problem, to our Teams chat or to PagerDuty, which calls someone in the middle of the night. So this thing is actually integrated very well, and that's pretty much where we want to aim. And this helps us achieve 2 things. One, we can look at a glance and say if anything is wrong right now. I can see that there was a problem in the past, but it's fine. It's over now. Seems fine. There was a load problem, and it probably got auto-scaled and fixed. All right, so this is something we can work with. And so from here, you want to go to automating this, right? The next step, obviously, once you have all this, you can go and you look at it. Looking at a dashboard is pool-based, right? You can go and you can look at it, but you can't be looking at it. Well, technically you can. If you're a big company, you have a NOC team, and they have big dashboards, and they 24/7 they look at graphs all day, which is a terrible way to make a living. But that's the thing that exists. Companies do that. Like our company does that. But ideally, what you want is you replace those people with robots or AI or whatever, obviously, right? Because I don't want to say a monkey can look at dashboards, but a monkey can look at dashboards. And so what you want is you want to build alerts and automatic triggers based on thresholds you define. This is not something that happens immediately, right? It's a system that's you're going to have to iterate on. You'll calibrate the threshold. Maybe you'll set a threshold too low or too high. And it's going to take you months to actually get to a place where you're happy with the alerts, because you don't want to have too many alerts. Having too many alerts for every little thing leads to alert fatigue, and you start ignoring them. At some point in the past, we had alerts sent by email. I had a mail rule, which just put all of them in the folder called alerts. And at the worst, I had like 30,000 unread emails in that folder. And it just tells you just how valuable those alerts were. So the best case is you want to have something automatic. Like you want to have an alert which triggers some sort of automatic remediation, which fixes the alert, and then just tells you there was an alert last night. You should take a look and see why it happened. So can someone give me an example of automatic remediation? Like what's a common automatic remediation for an alert? Turn
it off and on again.
Perfect. Turn it off and on again. I hope nobody would actually do that in production, but actually it's a thing we did in the past. We don't do it anymore. I mean, in some cases, for example, if you use third-party libraries, you don't control it. Yes, sometimes you have to turn off the server and bounce the service. It's usually it's usually kind of a code smell. I don't know if there's an equivalent in DevOps. Is there like a DevOps smell? But if you have to bounce the service based on an alert, it's probably not the best way to handle it. You should probably look and figure out why you have to keep doing it. But another common case would be scaling things out and up, right? So auto-scaling, you look at the load. If the load goes up above 80%, you scale the service. You scale it out until the load goes down to, let's say, 60%, right? That's pretty common. All cloud services give you auto-scaling for most things. The tricky part here is just defining what parameter you use to scale out. If it's CPU, great, but most services aren't really 100% CPU bound. Sometimes there's I/O and all kinds of stuff. So trying to figure out when you scale out is tricky, but if you do, auto-scaling is one of the common ways to actually do this. There's a bunch of different examples, and ideally, that's where you want to aim, right? Once you have good visibility that's pull-based, right? You can go and look at the dashboard. You want to make it push-based. When something detects an alert, it automatically remediates it. And there's a whole bunch of cloud companies which provide these services. I don't want to mention names because I'm not selling any of them. But if you Google for observability or metrics, there's a bunch of companies which will take in your metrics, apply some machine learning to them, or AI, and then spit out a bunch of alerts and do stuff for you, so you don't have to build it yourself. I say machine learning in quotes because it's usually just find the anomaly with linear regression. It's not like truly hard science. Anyway, so that's where we're going to go, and that's pretty much what there is with metrics. You can get a lot of good stuff with metrics. I highly recommend if you don't have like a one-view dashboard, you go towards that, add a bunch of automatic alerts, and that's pretty much the evolution you want to have in a system which doesn't have this or doesn't have good automation and observability. You want to evolve towards that. So the next thing that we talked about is logs. I'm not going to dwell too much on logs. Logs are very well understood. The main benefit of logs is they're very granular. They have high fidelity and high granularity because you go into a line of code, you print out a log. You can add a bunch of contexts. If it's an exception, you can add the whole stack trace. You can have a lot of detailed information from a log line. The main problem with logs is there's just a lot of logs, right? And it's very expensive to store all of them and index of them. So at one point, we had a massive problem with overlogging. And this happens when you have low confidence in your system. And if you have low confidence in your system, you're not sure if stuff is going to break in production. What normally engineers do, because engineers have very good imaginations. We can imagine all kinds of scenarios of stuff breaking. right? And we can imagine them, we can go, oh, well, maybe I'll add a log line here just in case this breaks. And over time, what happens is your production system gets filled up with log lines that are just in case, right? And you have to collect all of those logs, and you have to store them, and you have to analyze them, right? And so this becomes very expensive. And the usual trade-off is either you store fewer logs, so you reduce retention, and so you don't have as much history, or you just pay a lot of money to store just tons of logs. And like, we had several cycles of actually going through all of our code and removing logs, or moving them down from like high to low criticality. Everyone knows the log level, right? So like error warning info trace for Java, for example. So we moved all the logs down at least one level, so we could have more retention on them. So right now we have retention of, let's say, 30 days for errors, 1 week for warnings, and 1 day for info and debug logs, right? And we don't have to pay so much for storing them. But the upside, obviously, is if you have a log and it indicates a problem, you have a lot of detailed information. You can zoom in on the problem, you can find it. The other problem with logs is they refer to a specific component, right? So a specific service got an exception, it put it in the log. If the reason for the exception is not in that service, it's not a specific bug in the service, but it came from 3 services away, you don't know it from the log. There's no way to tie one log to another. There's no context that's passed between them. Every service that exports its own log messages, it exports its own metrics, right? And this is where we come to tracing, distributed tracing. So going from logs to distributed tracing is actually very straightforward. We built our own tracing system. Don't do this, by the way. I regret this. We thought we were too smart, so smart, better than everyone else. And so we said, we'll build our own tracing system with blackjack and hookers. So no, don't do that. These days, there are off-the-shelf products which do this for you. If I was building the whole thing from scratch, I obviously wouldn't do this, but historically that's the way it evolved because we were under a lot of pressure to fix stuff in production, and so we took a lot of small incremental steps instead of just one big one. We can argue about whether it's right or not. So the way we added tracing to our system is we had very extensive logging, obviously, and we said, okay, well, traces are kind of similar to logs. It's just the main problem we have to solve is how do you propagate context across services? Whether it's microservices, REST services, or Kafka-based or queue-based, whatever, the transaction usually starts in one service, and then it goes to another service, and so on. And you want to maintain the whole path, so you can take all these different logs from different services and say, these are part of the same transaction. Like this log and this log are from the same transaction, and so if there's an error here, we can look at this log and figure out why the exception happened, right? And so the first thing we did is we added a transaction ID or trace ID that was generated at the edge of the system that was bringing in the data from the API. And then we took the transaction ID, put it on the actual message itself, and it propagated from one service to another. So it was on the actual data object, which is not the best way. It's kind of dirties your data model, but that's the way we did it. And so every time we put a log out in every service, we would take the transaction ID and put it in the log. That's technically, it works. Obviously, we used it. It works. Obviously, it's a lot of effort. You can go to every service, find every line of logging, and you can add this transaction ID to the log. It's a lot of effort. It's a lot of code duplication. Not a good solution. I don't recommend it, but I'm saying this is essentially what you want in a trace, right? Because now, once we did that, we could go to our Elasticsearch. We could look at an exception log from one service, see the transaction ID, search for the transaction ID, find all the other logs which relate to this exception in all the other services, and now we had a much more complete picture, and we could actually debug problems that were caused in one service and propagate it to a different service. Right, and over time, we built more and more functionality on top of that. Eventually, we reinvented one of the common off-the-shelf tools. So we added timestamps to this, and then we gave names to the different spans between services, so we could actually identify where it came from. Right, so the span would, so if there's a service, let's say service A and service B, the span is what happens between them. So, for example, the REST request or passing a message. And so we could measure how long each one of those took. And so over time, we built more and more functionality into this. And eventually, we had very, very comprehensive end-to-end distributed tracing in our system without actually using a distributed tracing product. Which brings me back to this, right? Observability is not about products and vendors and buying stuff or using products. It's about we had a goal. We wanted to figure out how to debug things across different services. And we built something that answered that goal, right? The technologies are they're not irrelevant, but they're secondary to actually fixing the thing, right? And so if you look at modern distributed tracing tools, and we'll look at some of the UIs and stuff like that in a bit, usually what they have is they solve exactly one problem. How do you propagate the context of the transaction from service to service, right? And if you're in a synchronous web-based world, that's much easier, right? Because you have HTTP, and HTTP has headers. You can put the information in the headers. And so let's say you have a web service which calls 2 other web services, and each one of those goes to a database and gets some data and responds, right? And so you have a whole tree of calls all going out and then converging back, and you have one response going out to the customer or to the client, right? And so if each one of those services, whenever it calls in a different service, just gives it the transaction context, it will go all the way out, all the way back, and you'll have a full log of the entire transaction tree. That's pretty easy. Now, if you have a asynchronous message passing, event-driven, CQRS, whatever one of these flavors, that gets much more complicated because you can't really have a consistent way to propagate the context from service to service. The good thing is that most of these technologies you use for message passing, Kafka, Kinesis, RabbitMQ, all of them, they do have headers. What you don't have is some automatic way of passing headers. You have to manually go and set the headers for all of them. But essentially what you do is, for every service, there are two communication paths. There's the inline path. Every service passes just a small bit of data, transaction ID, and a few little bits of context from one service to service, because you don't want to pass a lot of data through. And then each one of them emits a bigger log with the transaction context and anything that you want to attach to it, like exceptions or trace information, stuff like that. Right? And so eventually you can go and you can create a graph of how your service behave, how your transactions behave. Like, so this, for example, would be a transaction where you have one service, service A. It goes out and calls service B calls C and D sequentially, and then it goes back to service A. It calls another service E, and then sends a message asynchronously to a final service, service F, right? And so if you graph the whole transaction, you can measure the time each one of them took. You can measure the time the transport took. You can figure out if there's a service that's slower than others and how it behaves. You can discover all the different dependencies between the different services. And this actually gives you a whole holistic picture of your entire stack. Right, so we'll actually look at a few actual UIs from real products and see how they actually graph it. Actually, let's do that now. So I'm going to show you one of the products that open source products for distributed tracing. It's called Zipkin. Let's run it. There we go. It's just a simple Java service, and what we do is we'll take a bit of code. Yes, this is .NET running Visual Studio on a Mac, just because I like being weird. And so this is what we need to do in order to add traces to our .NET application. Right? It's actually very little code, because it's a simple REST-based service. The application is in 2 parts. There's the backend service and the frontend service. The backend service, let's take a look at the backend service. It doesn't do anything. It just returns the current time. And every 1 out of 3 times, it throws an exception. It's a very simple backend service. The front-end service is not much more complex. All it does is call the backend service and then prints it out in the UI. It turns it to the UI, to a web browser in this case. Right? And what we do is we want to add distributed tracing. I want to know if the request from the front-end service got to the backend service, how long it took, were there any errors, and I want to graph the whole thing and show it in a nice waterfall model. Right? And so in order to do this, we're using a library called Zipkin.net. It supports a standard called OpenTracing. OpenTracing is a set of common APIs, which are vendor neutral, and they let you instrument your application and add traces without being bound to a specific product, right? So it's very similar to the way logs work. Like today, if you want logging in your application, you add, log4net or log4j, and you don't care what backend service actually stores the logs. If it's Elasticsearch or Splunk or whatever, you add one library to your code that knows how to instrument logs and put them out, and what happens after that, you don't care about it. That's the whole point with OpenTracing. All it does is it takes the tracing context and moves it from service to service automatically for you. It knows how to integrate with different frameworks like .NET and Spring and Java, and it does most of the work for you. And so all you have to do is actually register it. So we create the trace manager. We can set the sampling rate. We don't need to send out every trace. We can say, okay, we'll send 1 out of every 100 transactions, because we want to store less traces. It's not logs. Traces are usually statistics-based. We want to measure latencies statistically. So we don't need to send every trace. We can send 1 in 100 traces or 1 in 1,000. And then we tell it where to send it. We'll send it to localhost and register traces and just tell the application to start using it. And so if you run this, and hopefully it actually runs, and that's obviously the issue with the live demos. You never know if they're going to run or not, but we'll hope for the best. And so we run this. And now we have our service running. We'll go and we do a few requests. It really doesn't do much. It just returns the current date. And sometimes it returns an error. And I'm going to just click it a few times so we have a few traces going on. I'm trying to hit one that isn't an error. There we go. And now we can go to Zipkin, which is the UI currently running. And then we can go and look for traces. And we'll see, I'll zoom in. We can see all the traces we collected. Right? And we can see the length. It automatically sorts them by the longest trace. Obviously, this first one is the longest because that's before the JIT actually compiled the .NET app. I almost fell. That was bad. And so when you click into the trace, you'll see this nice waterfall graph. And you can see that the top service took this long, and the second service is called took this long. And you can trace into them and see all the parameters. You can see the error, right? If it was an actual stack trace, you'd get a stack trace. And if it was a long chain of services calling each other, you'd get the whole chain, the different timings, stuff like that, right? And so this is actually very useful. I can go and I can trace into my system and figure out what happened all the way along the chain of execution. It would actually look more or less the same if it was asynchronous, like if there was a Kafka message in the middle, except it wouldn't look like a pyramid. It would look like several pyramids. So the messages would be side by side, not one under another. And so we can also go and look at our system graph. It's pretty simple. So we have one service talking to another service, and we can look at the last 10 minutes of our system and see what messages passed. You can zoom into one of the services and say that, yeah, this got 9 normal responses and 7 errors. I have no idea why it's behaving this way. It's some weird web stuff, which I'm glad I don't know about it. Someone who does front end, please fix it later. Yeah, zooming doesn't help. But normally, you can actually see it. And the point is, if you have 50 services in your application, if you have 60 services, you can look at how the data flows between the services. You can find hidden dependencies. You can click on the trace. OK, this bugs me. I'm going to move it. Like, you can go. I think we're done with Zipkin for today. But you can go and you can look at it. I'll show you another example much better. This is from Amazon's X-Ray. You can go and you can look at hot paths in your system. You can find where latencies are. Some of these off-the-shelf tools actually give you a way to compare them. So there's a tool called Jaeger. And what it does, it can actually compare two traces. So you can find regressions. Like you can take a trace from today or a set of traces from today. Instead of traces from yesterday, you can look at them side by side and you can see that, OK, well, this one service now increased in latency by 8%. You can go and you can see, OK, so the average trace in this specific component changed. We can figure out why the regression happened, right? So this isn't anything new or novel, but it gives you new ways to look at your system and find out weird relationships between different components of the system. Right. That's pretty much all I had. I appreciate you very much coming. We have some time for questions. I'm happy to answer. If you don't want to ask questions in front of everybody, I'll be over there and I'll answer them in private.